Thank you very much for attending the talk. We'll be talking about porting, but mostly re-implementing the Xen PVHVM drivers for OpenBSD. And my name is Belopuhov. I have been an OpenBSD developer for about 7 years, give or take. And currently I'm working for SDNR Networks in Germany, and we produce networking appliances. And recently I've been tasked to produce a minimal but still functional implementation of PVHVM drivers so that we could run in the Amazon AWS cloud, but also to be able to support our customers. And I cannot stress more because without intricate knowledge about the drivers, the infrastructure, it's very hard to debug problems for customers, especially on site. And when we have this knowledge, then we can reason much better about potential issues or what customer might have a problem with, what the customer's problem might be. The requirements for the project, obviously, we need to be able to boot in the EC2 and Xen. Thankfully, it already works. We need to be able to mount root partition, to be able to read our kernel, to be able to start the initialization framework, and later system daemons and so on and so forth. Thankfully, it already works as well, because Xen and EC2 both provide a legacy PCIe compatible driver, so we don't really need to do. I didn't have to do anything really in order to be able to perform this task. To support SMP, and that didn't work on IP64. The reason why it didn't work on IP64 was because due to the fact that the LAPIC timer, it's a timer that is contained within every CPU core, is enabled quite early in the boot process for the purposes of delay functions, so that we can measure time intervals between two actions usually required in a driver initialization before we are able to do interrupts. So we enable this timer early on, but we do not enable interrupts until we are finished with device attachments and we are ready to kickstart the kernel threads. That creates a quite big gap between these two events, and by default what Xen does is that it delivers you a bucket of missed LAPIC timer interrupts right at the moment where you enable the interrupts, or in fact in OpenBSD kernel that means when we go from SPL high to SPL 0 at the end of the initialization process. And this amount of interrupts eat up your stack due to the bug in the LAPIC timer interrupt processing. There are some STI instructions that enable interrupts sprinkled around the interrupt handler that should not be there, and they prevent this interrupt recursion. And interrupt recursion happens and eats up your stack. That was fixed shortly, and the next thing that we needed to do was to perform cloud init. Cloud init is something that when a virtual machine is started in the Amazon cloud, you don't have any other access to it apart from the networking. And cloud init is a set of procedures that allow you to connect to the VM via network, such as by SSH. And that requires obviously the paravirtualized networking inverter, because Amazon Cloud does not provide legacy networking interfaces. Logging into the system via SSH, same thing. Then we started looking, and obviously the first thing we looked at was the FreeBSD implementation. I did look at the NetBSD implementation, but it appeared to me that NetBSD implementation is mostly dealing with the PV mode, the paravirtualized mode, where the kernel has to perform much more Xen-related operations in order to start and get into the paravirtualized driver LAN. FreeBSD implementation, however, contains both PV and the operation in the HVM mode. When we start looking at the FreeBSD implementation, what immediately struck us is that it's enormous in size. A bit of statistics. If I just run du on all files and directories that I used to implement Xen supporting FreeBSD, it reports me 1.5 megabytes of source code. Current OpenBSD implementation that is not by any means complete, however, provides enough support to be able to run the EC2 is just 128 kilobytes. I can expect this number to double or maybe triple when we support a few additional features, but I do not think that we will ever reach 1.5 megabytes. And statistics regarding the number of files on the slide as well. The implementation is also needlessly complex. First thing that you find is that guest initialization is a very, very simple procedure, at least for the HVM host, guests, I'm sorry. And in OpenBSD it's implemented in 2.3 function calls. FreeBSD has 2.3C files to do the same thing. The Xen Store API is taken almost directly from Linux. Implements things that you don't really need to implement. You can implement them in a much simpler way. Interrupt handling has very strange API and does not, in my opinion, does not abstract things very well. It can be done much simpler, and I will have a few slides about that as well. Clash of coding practices. Because Xen is a Linux project and a tiny bit academic project, it has a very different style, coding style from the BSD source code. And you immediately realize that this is not native code. And no wonder, because lots of code has been taken verbatim from Linux. And the other thing is a number of questionable abstractions, such as code generating macros. For instance, define ring type. I'm a big fan of command-based myself, but I do not consider CPP to be nearly effective as def macros. So I do not really think that define ring types and such macros that generate you a whole bunch of ring primitives actually needed in order to implement these drivers in a clean and comprehensible way. I will be talking a bit about Xen Store, but I would like to mention that Xen Store operates on ASCII strings, and there's a whole bunch of primitives that mangle these strings in order to create larger strings, and this is all done in the kernel with the use of with tons of mallocs, use of scanf to parse single-digit numbers. Most of the cases when we need to get a property, to read value of a property, we need to know whether it's 0 or 1. Most of them are flags. Most of the properties that we need to read are flags. scanf is definitely an overkill in such situation. It can be done through a simple char comparison. Therefore, porting plans were pretty much scrapped in the very beginning, and we sort of started finding the bits and pieces that were required for the next step in order to implement more and more PVHVM support. We arrived, and it didn't really. We didn't really plan to do that, but it turned out that the single device driver model was actually most appropriate. There's still a bit of separation between the Xen store and the Xen driver, but it's arbitrary at best. And in OpenBSD we have a PV bus layer that Raik has been talking about yesterday. It basically is a loop across the HV signatures that you can find in CPU ID, and within this loop PV bus layer figures out what hypervisors you have active and pre-initializes the attached arguments, and then through the autoconf machinery, if you have your Nexus devices configured such as Xen, you will get it attached at some point. PV bus also can perform some initialization of the system depending on which type of hypervisor you're using. For instance, on Amazon, we had to disable X2 Epic support in order to be able to get interrupts. I must say that we didn't spend too much time analyzing the problem, but we figured out early on that we could just make PV bus take care of that very early in the boot process before we even initialize X2 Epic and disable it on the system. All the other devices, all PVHVM devices, are attached to the Xen Nexus device itself. We don't implement a Xen bus abstraction like many other operating systems do, because in fact Xen bus abstraction in FreeBSD, the only thing it does this device state transitions, and that can be implemented anywhere else. It doesn't matter. So let's briefly take a look at the HVM guest initialization procedure and see. I will only point out the changes that we have in OpenBSD compared to other implementations. The Hypercall interface in Xen is akin to a syscall interface in a sense that you have a particular ABI that you have to follow in order to issue those hypercalls. And hypercall itself in Xen is a synchronous function call, meaning that the caller gets the return value right after the hypercall is returning, just like a syscall. This is not always the case. Hyper-V hypercalls, for instance, are asynchronous. That's why I'm mentioning it. Hypercall interface in Xen requires you to, the ABI requires you to specify parameters as registers and, well, most of them registers. I think in some cases, if you have a 5-parameter hypercall, you might be using a possibly stack. I'm not sure. I think on MD64 it only uses registers. The difference in OpenBSD in implementation of hypercall interface is that we implement a single function with variable arguments that can perform any hypercall you want, you specify, instead of creating about 20 macros that basically do the same thing but specify parameters in their name. For instance, if you want to perform an event ops hypercall, instead of saying Xen hypercall, you would get something like Xen event op hypercall. I kind of thought about doing the same, but then I just got this working and it turned out to be sufficient for all my needs. The hypercall page, this is just for those who are curious, essentially. What is a hypercall itself? Well, hypercall itself is just essentially it can be thought of as calling a function through a function pointer. There is a table of function pointers, essentially, in memory, in kernel, that is filled in by the hypervisor itself. We have to communicate the location of this page with the hypervisor, but once we've done that, hypervisor fills in the content, and whenever you issue the hypercall, one of the parameters, the operation parameter, actually serves as an offset in the page to select particular piece of that page to execute. The page itself is part of the kernel code segment. In OpenBSD, unfortunately, we do not have a way of allocating executable kernel memory. Partially, this is due to the fact that the memory layout of kernel is structured in a way that allows us to use 32-bit relative jump instructions in the kernel that prevents us from jumping anywhere except for the upper 4 GB. It's actually 2 GB because of the memory layout of the kernel. And we lack a way of allocating memory in that particular region of memory. In fact, one of the first things I did in OpenBSD was to fix LKMs on MD64, and I did that by creating a map in that region of the memory and allocating pages from there for the LKMs. LKM is a loadable kernel module. But with LKM support drop, that map was removed from the kernel. The hypercall page is filled with knobs. This is what 90 hex says. 1000 hex is a page size, and we export the symbol Xen hypercall page into. We create an entry in a symbol table and provide a C code with a reference. If we just look at the hypercall page itself, it basically looks like this. We define the hypercall by the first instruction, which moves 0, 1, 2, 3, and so on and so forth into the AX, and then the setGate instruction just produces a VM exit event that hypercall, the hypervisor catches and performs the whatever operation you have specified in the registers. And then it returns, and the rest of the page is filled with in3 that is usually used as a debug interrupt. The second step in guest installation is shared info page. Shared info page is a rather interesting interface, and we do not implement it. Well, we obviously implement we obviously map the shared info page, but we do not implement the per CPU. We can basically, part of this page can be made per CPU. We don't really need that at the moment, but eventually we'll get that too. Shared info page contains a matrix of event bits. Whenever, well, I'll get to that a bit later, but basically whenever an event for one of the devices is triggered, the hypervisor sets a particular bit in the event matrix that is reflected in the shared info page. It also provides access to the PV clock. It's a shared with KVM interface for time counter. We actually don't support it. I'm looking into supporting that now. The interrupt subsystem in Xen is actually very simple. There's a lot of I had to spend quite a bit of time trying to go through the FreeBSD code, but in essence it's very simple. The first thing we need to do is to allocate an interrupt descriptor table slot. The way interrupts are implemented in x86 CPUs is that the system software, like an operating system, installs a gate into the IDT, and it specifies in a particular way which function it needs for CPU to call, and CPU calls that function for the operating system when the interrupt is triggered. IDT usually contains 256 slots. We predefine vector 70 hex. It says here it's a start of an IPL net section. The thing is, in OpenBSD we still use interrupt priority levels, although in AMD64 they're implemented purely in software. But the IDT table itself is partitioned into sections for different IPL levels. And we just pick the first available vector in the IPL net section, meaning that all of the Xen interrupts are executed under IPL net. It's the highest required interrupt priority level for Xen interrupts. IPL bio that we would use for the disk interrupts is actually lower than IPL net, so we don't need to go anywhere higher. Right now it's pretty fine, so it's static configuration in the kernel, but I would like to, especially with Hyper-V code, to move to the dynamic allocation of an IDT vector. The second step is obviously to prepare those the vector itself that we want to put into an IDT slot, and this is called Xen call. The Xen call is the entry point for a Xen interrupt. Xen interrupt uses one single IDT slot and for all the devices, and then it fans out one interrupt into a number of events through the event matrix. We also have to one of the other differences to FreeBSD is that we actually have support for pending Xen interrupts. It's done purely in software. There's no real hardware bits needed to implement that, due to the fact that since we haven't really migrated to a proper SMP world of interrupt processing, we actually do a bit more work in the interrupt handler than FreeBSD does, and I kind of kept this model for Xen as well. Pending interrupts allow me basically to do printfs from interrupt handlers and things like that. And obviously they also allow me not to lose potentially Xen interrupts in case the IPL level is too high. Then we communicate the slot number with the hypervisor, the IDT slot number, and Xen basically can start injecting the interrupts into the guest via this IDT slot. An alternative to injecting using the statically allocated IDT slot for Xen interrupts is to use so-called Xen source platform PCI device driver, XSPD. It serves as a backup option for us right now, but I think it plays a a bigger role, a larger role, once we have the PCI interrupt pass-through support. But basically it's a PCI device, and all it does is establishes a PCI interrupt that we communicate to Xen as an alternative to the IDT, to the simple callback vector. The API itself that device drivers are using is modeled on pretty much any other interrupt establishing API that we implement in OpenBSD for many different platforms and bus variations. It takes what is called the event channel port. It's the Xen way of saying that bit in the event matrix. And a Xen interrupt handle T is an interrupt handle abstraction that we use in OpenBSD for different buses and so on and so forth. But in Xen, it doesn't actually serve any purpose except for storing the value of event channel port. The reason why we have to provide event channel port in the Xen interrupt established is that some devices do not want you to allocate a new event channel port. They come with predefined port like the Xen store does. In that case, you can specify that and it will handle that situation. In FreeBSD, it's implemented by two different functions that have slightly different semantics. Mask and mask. Mask is cheap and mask has a hypercall, so it's not as cheap, but mask is just a twiddling of bits in the shared memory, in a shared memory buffer. Event fanout itself, I have created this small diagram because I didn't have enough space. I'm sorry if I have offended purists. So basically what I wanted to say is that Xen interrupted call is called by the CPU, it's programmed into ADT. The only thing it does is calls, except for IPL logic that it has to raise the APL, check the APL, raise the APL, and so on and so forth. It calls Xen inter function, that is the interrupt fanout. And while there are any pending events in the matrix, we look through the matrix and we look up the interrupt source by that bit, by that bit that is set in the matrix. We find the interrupt source or not. In case we find it, we run the handler with a provided argument that we provided in the interrupt establish the argument. This code in OpenBSD is 37 lines long, and FreeBSD is over 100. Does the same thing. So, with interrupts working, we are almost there, except that we need Xen store. There's no way around this beast. The reason for that is that Xen store, it can be thought of as a key value storage. In fact, it's a bit more than that. It's an interface that uses a shared memory buffer. You can call it a ring if you will. It's just it's essentially a 1 byte, 1 kilobyte contiguous buffer for input and 1 kilobyte for output with a producer-consumer indices. It's driven by interrupts. We do support polling as well because we start up Xen very early. It exchanges ASCII null terminated strings, which is kind of bad actually, because you have to do all these manipulations and you have to do all those strlens and more importantly, you actually have to convert all your numbers to strings. For instance, when you read a MAC address, it's a string, you need to convert it. When you read a value, it's a string, and if you want to interpret it as an integer, you need to convert it. When you set up your ring in your networking interface, the way I will show that later, but basically you need to take a number and convert it to string and send over the Xen store. It exposes a sort of a hierarchical file system-like structure where you have you're basically like a home directory that is called basically the only thing that is visible there is a device. On the DOM0 side, Xen store contains configuration for all currently running VMs plus the DOM0 itself. This is an example of what you see in your home directory. It's basically the part that is accessible without saying /local /domain /0 in this case, because of the backend. This is a reference to DOM0 path key. And for instance, if you will look at the Xen store structure, every node in Xen store structure has associated permissions with it, and we cannot, as a guest, read every single value there. We are provided access only to a few bits. For instance, this is a backend configuration of our primary networking interface on some EC2 instance. It provides some feature flags, some state flags, and so on and so forth. Device discovery is done through Xen store. We'll loop through the device node, finding the second level elements like VIF, VVD. Then looking inside of them yields us actual interfaces, like for instance VF0, VF1, or VVD. And taking all that information together, we basically create an attached argument structure for the configuration framework and attach individual drivers for corresponding to particular nodes on the device. So, we're probably ready to get to the networking part, but in fact we're not, because the first thing you need to do is to allocate your rings, and you need grant tables. Let's quickly remind ourselves of how does a simple ring works. Well, it's regardless of whether it's a RIX or TX ring, you have a notion of a descriptor. Descriptor is a metadata that points to some part of memory, and descriptor is visible to you as well as it's visible to the device or the hypervisor. And you have producer and consumer indices. In the beginning, they all point to nothing, point to the first element, meaning that the first element that you produce, when you produce the first element, meaning you attach a buffer to the first descriptor, you need to increment your producer index, like that. Like that. And once at this point, the device has produced two buffers, and it signaled the other side, hey, I have two buffers of memory for you to process. The device wakes up and adjusts its consumer index, telling you, hey, I have consumed two descriptors. We have produced another buffer and another buffer, and now we have, once consumer told us, once consumer index is adjusted, we can take those buffers off the ring, we can deassociate them with the descriptors, and free them or do whatever we want with them. Now when producer reaches the last element, when we produce the buffer 5, we need to make sure to wrap it. Same with the consumer, and we get that. So let's take a look at what does it mean what does descriptor actually do? Well, it needs to point to physical memory. If we are talking about devices, it needs to point to physical memory. When buffer is allocated, we normally allocate both physical and virtual memory at the same time. The virtual memory and the physical memory are connected via the physical mapper module, and the translation between virtual address and physical addresses is done by the CPU and the MMU unit. For instance, we take a buffer that is found as a fourth page in the system, and it has this funny virtual address. If we want to map CPI into the buffer in the kernel, we have to use the virtual address. If we want to connect this buffer to a ring descriptor, we need to use the physical address instead. And the way we do it in BSD is via the bus DMA interface that was implemented by Jason Thorpe for NetBSD project, and since then it has unified different approaches to DMA memory management across different architectures and devices. And I have to go a bit into bus DMA details here to show how I'm using it in Xen. And the important part, I have highlighted only the important bits. And the way you use bus DMA interface is that, first of all, you create a memory layout with bus DMA map create. You're creating a map. You're specifying the size of the map, the number of segments. I will get back to it. For instance, at least one segment. And the buffer we've seen there is, we can consider it a single segment buffer. And that's the segment. And segment describes the buffer in terms of an address, a physical address, and the length of a segment. Then we need to allocate a buffer of memory usable with the DMA interface. It's commonly done by bus DMA memlock. It can be allocated in any other way. It doesn't really matter, as long as it fits the requirements of the interface. We can map it. We need to map it into the KVM. The reason for that separate step is that bus DMA memlock usually allocates only physical memory. It does not allocate virtual memory. Bus DMA map can map it into the kernel virtual memory, kernel virtual area, so that you can perform your memcpy operation in this region. And this is an example of buffer spanning 2 pages. We have 2 pages of memory, completely different physical addresses, 3,000 and 5,000. And we want to have a contiguous buffer. We want a memcpy from here to there. The reason we can do it is because we can just allocate contiguous virtual memory space and map these 2 different memory pages into that space and tell the device, hey, there's 2 pages of memory, 2 segments that I want you to work with. And the way we are doing that is via bus DMA load. We connect these 2 segments to the memory layout, to that segment structure that we have allocated. Like that. Segment points to that address, segment 2 points to the other address. And then we are ready to signal the other side to start the DMA transfer, because it has access to those. Okay. Once we've done that, we need to. Once we've done this loading operation, we have these segments filled in with physical addresses. Now we can take those addresses and put them into the descriptors on the ring and signal the other side to start the DMA transfer. Once the transfer is completed, we have to disconnect those memory buffers from the segment structures by just clearing the values. We'll map it from KVA, for instance. If we want to dispose of the buffer, we call the free function. And then if we want to destroy this whole layout thing, we can call busDMA map destroy. That front RX string consists of a 64-byte header and a power of 2 number of 8-byte descriptors that fit into one page of memory. That basically gives us this: 256 descriptors and a bunch of indices. The descriptor itself can be thought of as a request or response depending when you look at it. When you're about to produce the buffer on the RX ring, when you want to prepare it for device to write into the buffer, we call it a request. Once the device or hypervisor has written into the buffer, it signals the completion, and then we'll look at it as a response. But it doesn't really matter for us at this point. We'll just look at the request. The request contains what's 32-bit reference. This reference is not a physical address. But let's take a look. How can we create this? How can we put that thing into memory, to shared memory via busDMA? We create a single entry because it's only one page. Single entry map. We allocate a single page. We map it into the kernel because we want to read it at some point or write into it. We load it into the segment map, and now we can communicate the location of this page with backend. Of course, this is not the final stage for RX string creation. We need to allocate the same structures, well, only maps for each descriptor, because each descriptor is normally a cluster in BSD system. It's an mbuf cluster that we allocate from the pool. But let's say we've done that, and now all we need to do, when we want to take a cluster that is a random chunk of memory in the kernel and connect it with a receive descriptor, we need to load it. Load extracts the physical address of the memory buffer and fills in the segment structure. And later, from the segment structure, we can take this address and put it on the descriptor. Except that descriptor does not use physical addresses, it uses references. To deal with this, we need to use grunt tables. Grunt table is a very simple interface. It's a multi-page IOMMU-like structure. Every page contains 512 entry, 8-byte entries, or 256 16-byte entries, depending on the version of the entry that we're using. We're using version 1, and it's an 8-byte entry that contains information about the physical address in the form of a frame number. Is basically, you throw away those zeros that in this table, and this is your frame number. Frame number is basically a number of a physical page, not the address, but the number of the physical page. Basically, it's a number of page-sized increments, right? So for a page of 3 with a physical address of 3000, the frame number is 3. For the page of with a physical address of 5000, it's 5. So entry 1 will point to frame number 5 with some permission flags. Entry 3 that we allocated will point to the physical address with a frame number of 3 that correspond to some contiguous buffer in the kernel memory. If only we could basically take that reference number and put into the segment structure because once we do that, once pass.dma load returns, we already have all those frame numbers in our segment structure, and then the driver can use that information without looking at it and treat it like a physical address or whatever address. Well, in fact, it's a ground table reference number. And it's very, very, very doable. It's actually very, very simple. Because bus.dma interface allows us to create our own bus DMA tags. Tag is just a structure containing function pointers for whatever function call you want. Create, load, and so on and so forth. So we override. In fact, we don't really override. We rob the system default methods with some Xen versions dealing with the ground table. For some methods, we don't really need to override anything, for like memory allocation, and some methods we don't really need at all. Therefore, they're all set to null. And bus.dma tag structure, as well as the map structure, contain a cookie pointer to store your private data associated with the map. We use that cookie pointer to allocate and store a small array that acts as a mapping between the references and physical addresses. We allocate this array at the bus.dma map create stage before we actually need to load or unload individual buffers. Once that's done, whenever we want to load buffer or unload the buffer, we can call a few simple functions that just twiddle bits and pre-allocated entries of the ground table. During unload, we perform the same operations backwards. We twiddle the bits back, we disconnect the buffer from a ground table, and if we need to destroy the map, we destroy the array as well, the mapping as well. Once the rings are created, we need to announce them to the hypervisor. It's done through a Xen store interface by setting Rx and TX ring ref properties. Once that's done, we've got our NetFront interface fully operational. We can go ahead and upload our image into the Amazon EC2 cloud. The way Amazon EC2 operates is that you need essentially to have a published machine image that you create out of a disk image. And that machine image cannot be OpenBSD default, cannot be OpenBSD installer image. The reason for that is that once you boot it, you need to be able to talk to it. And the only way you can talk to it is via SSH. And well, I mean, therefore you need to obtain the keys that you specify in the Amazon Web Interface. And due to the fact that the image itself is also a root disk at the same time, we have not provide installer images. We have provide installed images with a few bits and tweaks that allow us to connect to the internal HTTP server to fetch keys and so on. The public images of our development snapshots and hopefully the upcoming release were provided regularly by Raik Flöter and Antoine Jacoutot in several Amazon availability zones. Antoine, thank you very much, has created a few scripts to automate creation, upload of to automate creation and upload of OpenBSD images into the EC2 and perform the cloud edit. And hopefully we will be able to provide the upcoming release in the marketplace. The biggest problem is that if you go right now and you search for OpenBSD on EC2, you only get community images, and I don't know, I'm not really sure what image I'm using when I'm doing that. And obviously it would be beneficial for us to have one particular reference image in the Amazon marketplace, even for such purposes. Of course, you can probably identify the image via the AWS CLI tool and something like that, but I don't think everyone would do that. The future work is to support the PV clock time counter. That's part of the shared info page, that's what I'm doing right now. Support for suspend resume. I skipped the power management piece. We do support shutdown, but we don't support suspend and resume, which could be useful. The driver for the disk front interface, also something that would be really nice. PCI pass-through. It seems like that the big Amazon instances basically slowly migrating towards towards hardware with virtual functions instead of using paravirtualized front. And I would like to thank Raik. I would like to thank SDNero Networks for supporting this work and coming up with this amazing project. And I'd like to thank OpenBSD developers for constructive discussions, and all our users who took their time to test, report bugs, and even produce some patches, encourage development. Special thanks go to Value and Roger from Citrix for being open to question and providing some really valuable feedback, as well as all the contributors to OpenBSD or FreeBSD and NetBSD Xen ports. I think that without their contributions, this work might not have happened at all. Any questions? Please.
I think that right now you are using the interrupt from using an IDT vector in order to inject interrupts into the guest. You said that you may want to migrate to the PC interrupt, or you use that as a fallback right now?
Yes. Correct.
But you're not planning to switch to using that as the default one or anything like that? Okay. And then you have one vector for each CPU, or you only use one CPU?
Currently we use only one.
Oh, so you cannot receive interrupts on different CPUs?
On OpenBSD, it's currently not possible. Well, I mean, it's not, technically impossible, but we don't do that yet. Maybe it will change in the next release, but I would like to do that along with changes in the rest of the system.
I mean, because if you use, for example, the PV clock, the PV time counter that you say, you can also implement per vCPU one-shot timer using the IDT vector, but then you will probably need to be able to inject interrupts into each CPU. Well,
that's correct.
Let us do it on real hardware first.
Yeah, because now you receive all the interrupts on the same CPU always.
Well, except for time interrupts.
Oh, timer interrupts, you can receive them on multiple CPUs.
Yeah.
Oh, so then you could probably do more or less the same for the same timer at least.
We can, yes. More questions? Thank you for attending the